This section is section 1.7 on inverse functions. We're going to start by reviewing what an inverse function is. If you think about it, if we have x minus 5, and so the operation we do to x is we subtract 5, and we go ahead and do the inverse operation where we add 5, what comes out but just an x? So here I'm doing an action, and then I'm doing the opposite action, and that's giving me an inverse function. Back in 151, we would do something like this, where we were given an f of x equals 8x and g of x equals 1/8 x. So f of x, let's try this again. Okay, so we do f of g of x. And remember, what was this? This was f of g of x. So this was our shove function. We would take our g of x and shove it into our f of x. So the result here would then be 8 times 1/8 x There we go, 8 times 1/8 x, which would then just come out and be x. And that was, using this composite function, is how we defined our inverse function. We're now going to do the same thing for trig functions. So let's start by just looking at our sine curve. Now, one of our rules for an inverse function is the function had to be 1 to 1. And we did a horizontal line. So if we draw a horizontal line through this, do we cross it more than one point? And the answer is yes. So this is not a 1-to-1 function. And if you remember, back in 151, it had to be 1-to-1 to have an inverse. Instead, what we're going to do is we're going to put limits on this function, and we're going to say that the function is going to run basically from here to here. So we're going to say for our sine, we're going to be from negative pi over 2 to pi over 2. All right, and that then becomes our function. So we're limiting it, and we're only going to look at this region in here. In essence, I'm ignoring the rest of the sine curve. Now, remember what happened with functions back in 151. What happened then? The domain became the range, and the range became the domain. If we look at this, what is our domain? Our domain is a bunch of angles, and our range is then y values. So what happens if you graph out the inverse function? The inverse of the sine function, now notice, our y values are our range, our angles, and our x values are domain. So if we're putting in, let's say we take the sine to the negative 1 of 1, what are we doing? We are putting 1 into this arc function, and what is coming out but an angle? So you can see from the graph, what comes out is then going to be a pi over 2. We're going to start putting numbers in, and out comes angles. You can think of your unit circle that we're doing it backwards. So let's take an example. Here's sine, and here's that negative 1. Now remember, or not, shouldn't say remember, I need to remind you, this sine negative 1 of x, all right, this does not equal 1 over the cosecant. The way we determine 1 over the cosecant, it would be sine of x to the negative 1. That would equal 1 over the cosecant of x. When the negative 1 is next to the sine, then we are dealing with an arc or an inverse function. So let's go ahead and take a peek at this. If I want to find the inverse, or I want to find the arc function of sine of 1/2, if we look at the unit circle, there's a couple of places where that pops up. Well, the first place is pi over 6. And as you're heading around the unit circle, you're going to see it's going to happen in quadrant 2 at 5 pi over 6. And then it's going to happen 13 pi over 6. If we head around the circle, now we're back in quadrant 1. But before we write these angles down, we need to remember that we are looking at the fact that our answer must be between negative pi over 2 and pi over 2. Because of that, there is only one answer to this problem, and that is the answer right here at pi over 6. Let's take a peek at the cosine function now. We're going to do the cosine function in a similar manner, only the difference is the fact that we're going to run the cosine function from 0 to pi. So this function here. All right, so our limits on this one is 0 to pi. So our y values can be between 0 and pi. All right, now the reason we choose negative pi over 2 to pi over 2 and 0 to pi is strictly convention. This is how you're going to need to learn it and remember it though. Let's go ahead and look at what this is. So here we go. Here's a graph of the inverse cosine function. Notice my y-axis now has the angle on it and my x-axis has the number. So let's say we put in 1/2. Let's look at 1/2. So if we put 1/2 in, and this would then be cosine of 1/2, what's going to come out? You would run this number over, and that should be, yeah, looks like it's pretty close, pi over 3. All right, let's go ahead and look at it as a problem though. For example, we just did this on the graph. We're now going to look at it as a problem. If we have inverse cosine of 1/2, what are our options? Well, one option is pi over 3. What would another option be? Where else is cosine positive? Remember, let's look at this just for a second. All, sine, tangent, cosine. So the other place where this could happen would be 5 pi over 3. But what did we just do on the previous page? On the previous page, we said that in order for us to find the inverse, y had to be limited between 0 and pi. And in order to make that happen, then there is only one answer, and that's pi over 3. Let's go ahead and look at the last function, which is the inverse tangent function. Once again, notice what's going on here. We have negative pi over 2 to pi over 2 is now on the y-axis. And the x-axis is unlimited. Remember, what are these? Right? What is this line here? This line here, when we graph the tangent, used to be our vertical asymptotes. It's where tangent is undefined. That's going to become what? As the inverse function, these are going to become horizontal asymptotes. So the same scenario would happen. Let's say we take the inverse tangent of 1. It's right about here. Come up to the side here and over. So that's going to be what? That's going to be pi over 4. We could also take the inverse tangent of negative 1, and that's going to give us negative pi over 4. So that concludes your introduction to inverse functions.